should be transferred to the target environment. So here we have the training environment, which is the simulation, and the target environment, which is basically the real job task. And its successful training should result in the transfer of skills from the simulation to the target environment. So the point here is designing these systems, or how to design these systems. How to build such a simulator in which the practicing with that simulator can develop skill in the trainee so that this skill can be successfully transferred to the real task, to the real world task. So if the task might be flying, driving, various other tasks, and then we develop a training system for that task, and then that training system should lead to the training of skills that are transferable to the target environment. Now the question, which is the subject matter of our presentation or our review, is how to design this, how to reach from the task to the training system. So traditionally, researchers and designers were involved in, the first thing that came to mind was simulating a target environment in the system, in the training system. So for example, if we have an airplane, then the simulated airplane should be something that looks like the airplane, that brings the idea that this is the simulator of the airplane in visual sense, in perceptual sense. And of course, there's the key concept of fidelity here, which means the level of similarity between the simulation and the target environment. So as an example, for example, suppose the task is troubleshooting an electronic circuit. Then the low fidelity might be a software because it doesn't look like a real circuit, for example. The mid fidelity is an example of the snap circuit, which is kind of a toy circuit that are used for training basic electronics to children, which looks like the target task or the real circuit, but still does not have all the features of a real circuit. But then we have a breadboard, for example, that looks more and more like the real circuit. So this is the range of different levels of fidelity that we can think of that might be used for the purpose of training. So this is what fidelity means in this context. So the traditional theory of design for training systems believed that the higher level of fidelity, which is more realistic simulation of the target environment in the simulation, results in better training systems. So in an influential paper by Miller in 1954, as we can see, the level of transfer and fidelity have kind of a relationship with each other. The higher the fidelity, the higher the transfer. But then because the cost of training systems or very high level of fidelity was too high, then the question was what level of fidelity is enough for the task? The result of this approach, which was kind of a traditional approach that ensued a lot of future research from 1950s towards the 70s and even until now, was that the problem of designing training systems became the fidelity question, which is what level of surface realism is needed in a training system. So a designer who is involved in designing a training system should only be focused on what level of realism should be implemented in the training device or training system. But then, in more recent time, after 70s, but specifically over the last 1 or 2 decades, there were a lot of findings that they showed that lower fidelity systems in various tasks might be as useful or even more useful than high fidelity systems. So in various fields like healthcare, flight training, or those domains that make extensive use of training systems, this was shown that there are various potentials for low fidelity systems to be used effectively for training. So, for example, in flight, we have a low fidelity system and a high fidelity system, which is more like an immersive environment, like an AR or VR systems. In healthcare, we have this kind of a toy example of a human, and then we have a higher fidelity, which is like a VR system. And in firefighting, is the same. But then in these specific examples, and other examples as we reviewed the literature, it is found that the lower fidelity systems were more effective. And the reason could be for various reasons. For example, the environmental or visual clutter or distractions might be lower in the low fidelity systems. Or focusing on the crucial part or relevant parts for the purpose of training might be easier in the lower fidelity systems compared to the higher fidelity. And there are various other reasons, but we are not that much concerned with the reason, but the fact that low fidelity systems are still useful and effective in training. And in another example, Smallman and Sanja call this as naive realism, just the reliance on higher levels of realism. That, for example, if you have a real-world case in which there are two fighter aircrafts, then the realistic icon, like high fidelity, looks like this, which looks like the target environment. But then a functional representation, which is a lower fidelity, is something that does not look like this, but still might represent more information. The question was, a functional question here was, for example, which aircraft is descending, which is headed east, which is F-15. In all of these questions, this is more useful in answering this question than this realistic one, of course. So there are a lot of criticisms. These are just examples in the literature that we should not just blindly rely on increasing the level of realism and fidelity for the purpose of training, specifically for the purpose of training. So we have this traditional theory and this later findings, that's challenging findings. But then we should just think about what we found in the literature. The entire goal of training is, of course, to make trainees behave or perform in the target task like experts. So in the two other side, we have the trainees and the expert. I have like a human shape here to focus on the human elements of this training cycle. And the goal is to transform trainees to perform like experts. So the training system should provide an environment in which trainees should practice to develop skills to become experts. And so in this kind of picture, we have training in one side and expert on the other side. What should matter in the design of training system, instead of surface realism or fidelity, is the characteristics of trainees, like age, background, prior skills, or various other characteristics that are relevant for the purpose of training. And in the other side, we can use experts through recording their behavior to see how they act, how they make decisions, and perform their actions. Through these sources, we can find a lot of information for the design. Unfortunately, in the traditional theory, these crucial aspects of the training science or relevance of the training aspects in which the trainees and experts should be the focus were not in the focus that much. Instead, scientists were more focused on the system, increasing the using the technological advancements and computational resources to make more and more realistic simulations, just like games. So the lesson in brief that we got from reviewing the literature was that the fidelity of simulation is not and should not be a reliable construct for the design of training systems. And of course, the goal or the method of manipulating or increasing the surface realism does not necessarily determine an effective training system. You might say that this is very obvious, of course, like fidelity that might not matter, and it highly depends on the task. But as far as I know, in my department, in my university, I still see funding coming from like military sources or various other sources that ask for, okay, what should be the level of fidelity? That's the wrong question, basically. At least our review of the literature showed that. It might matter, but only after we consider the crucial aspects of the training, which is, again, the trainee and the expert. So